Hey friends, welcome back to the studio. On this video, we're going to look at building with accelerometers, which are part of the hardware facet of the mobile ecosystem. So accelerometers are quite common in modern devices, and you probably have used several every day. So they're basically small sensors that measure acceleration. What acceleration is just essentially how quickly something's speed or direction changes, okay? That's what acceleration is. So think of it like having a marble in a box. When the box tilts or moves, the marble shifts as well, right? And that's what the sensor detects, that change of shifting. Now, before we get into the coding side of things, I just want us to appreciate the use cases of accelerometers, starting with in smartphones. In smartphones, we have three use cases. For example, the screen rotation, that's because of the accelerometer, step counting or pedometers, which we're actually going to create that use case where we track steps. And then we have shake gestures. Shake gestures you might have seen in certain apps where you're asked to shake your phone, and that motion is what triggers a specific feature. So the ability to do that is by communicating with the accelerometer of the phone, or the code communicating with the accelerometer of the phone. Another sector will be the wearables or the fitness trackers. So, one of the use cases is activity tracking, as you've mentioned, where you detect walking, running, even sleep movements. That's with the help of accelerometers. And also fall detection, where the sensor reads a sudden sharp acceleration followed by some form of stillness. Then it will trigger an emergency alert. You may have seen this as one of the features on many health kits. Great. Another sector will be laptops, and in laptops, one of the use cases is hard drive protection, where the accelerometer detects a sudden fall and then it packs the drive head to protect the data that is there. Then we have gaming in terms of motion-based gaming, where accelerometers allow the controller to act like steering wheel or a sword or maybe a tennis racket, depending on the game you're playing, right? Another Another sector will be automobiles or vehicles, where some of the use cases are the airbag deployment. So when the accelerometer detects a sudden deceleration now, like in a collision, it signals the airbag to deploy. And also another one will be navigation systems. Yeah, so those are some of the use cases, and you find that the calculation that is made whenever we get the accelerometer readings from the phone depend on the use case that you're going for. For the calculation in fall detection will definitely be different from step counting, right? So before we get into the exciting part, how do accelerometers work? So inside an accelerometer, which is in your phone, it's um it's basically they're tiny plates that move slightly when the device shifts. So whenever the device shifts, they're capacitive plates that actually move slightly. So the movements are the ones that alter electrical signals, and then they're converted into acceleration values. And those are the acceleration values you'll get to see on the code. And the values are on the X, the Y, and the Z axis. Great. Let's proceed to the tutorial. So now in our code, we're going to interact with the accelerometers on our device. So I have a simple empty app that only holds the text widget. So where we're going to start, if you are familiar with Flutter, you already know what this is. We have the main function, the main method. This is the entry point for the app. And then we proceed to call the run app method, which is the one that will start the app, as we have seen right now. And inside our material app, we have our text widget here, which we're going to replace it with our main screen widget. So let's design our main screen widget first. So it will extend the stateful widget, and we're going to call it the step tracker. Inside here, let's just pass in a scaffold, and then we proceed to call our step tracker and replace it with a text widget. Great. So now we have an empty scaffold. Let me just proceed to add some theming. Great. Next, we're going to remove the banner that's on the top right. Great. Now we have a clear black scaffold with nothing. Now let's add, before the next thing we're going to do is look at now the logic. Any logic that interacts or involves in helping us interact with the accelerometer before we get into the UI. So inside our step tracker, we're going to define a few variables, and we'll go step by step. But before we proceed, make sure that you have installed 3 important packages. We have the Sensor Plus, we have the Shared Preference, and the INTL. The Sensor Plus is the one that allows us to interact with the accelerometer on the device. The Shared Preferences is just for local storage. We're going to store some of the steps of the day inside our local storage. And then the INTL is for formatting dates, or the current date that we read. We just want to display it in a much more user-friendly way. So it's not really relevant to accelerometer implementation. Great. So back to our code. Now we'll define some few variables that we're going to need, starting with a step count. So I'm going to give it of type int, and I'm just going to call it step count. So this is the one that's going to change based on the total steps someone has taken for the day. So currently we're initializing it to 0. The next thing the other variable that we need is our daily goal. So we're going to set it as fixed in the code, but it will be a good challenge to actually create a way in which a user can customize their goal. But in this case, we're just setting a fixed value. So we're just going to give it daily goal to, let's say, 5,000. Great. The next thing we're going to do is we're going to have a variable that will hold the last time a step was counted. That's where we need also the INTL package. So we'll have the date time, and then we're going to give the name of our variable as the last step time. This is mainly for display. Great. Another variable that we need is a variable that will hold milliseconds that we'll need to add it into there's a implementation that we'll do specifically for calculating the accelerometer readings that we get from the device. But now the idea is we don't want to just pick every reading in every second. We want to give a buffer, okay, and a buffer of a number of milliseconds. So we want to initialize the milliseconds that we want to buffer with into a variable, then we'll use it inside the logic. So I'm just going to define it as of type int, and then we'll just give it around 350 milliseconds. You'll find me repeating the logic of accelerometer calculations of accelerometer readings as we go on, so don't worry about understanding. You'll get to understand further the more I repeat it. Then the last variable, or another variable that we may need, which is not related to the accelerometer but more on the interface, is we'll need to set the date, the current date, type string. We're going to define it as we continue. That's why I've added the late keyword. Great. And now let's get into now the variables that we'll get to use a lot with the accelerometer, apart from the step cooldown seconds. So the cooldown is, what your cooldown means is just the number of seconds we want to prevent us from the buffer that we need to put before we read another reading that will define another step. That's why we're calling it cooldown. Okay, now another variable that we need is of type stream subscription. So we already know accelerometers measure the velocity of the device, either the speed or direction, okay? So what happens is that when we read from our phone, we get data of type accelerometer event. Accelerometer event is a data structure type, okay? It's just the way you might set your data in a data structure like a list or an array in other languages. So what is going to come the data structure that's going to come will be of type accelerometer event. And that data structure will hold 3 values, an x, y, and z value. But let's go back to defining the variable. I mentioned that it will be of type stream subscription. So it will be coming in form of a stream. So we'll always be listening to the readings that are coming, and we're going to be collecting them, and then we work or interact with the reading or the accelerometer event data type that we have received and perform calculations on it. So as I said, we'll have a variable of type stream subscription. Okay, and then the data type will be of type accelerometer event. Okay, and then we're going to give it a name of, let's give it accel sub, and I'll just set it as nullable for now because we are not initializing this here. So this will be our sensor listener, but we're not going to initialize it here. We'll initialize it later on. So let me repeat what I said. So this accelerometer event holds 3 values, x, y, and z. So the x value is the accelerometer reading that reads the acceleration along the horizontal axis. The y is along the vertical axis, and the z is the depth axis or perpendicular to the screen. So we need those 3 values. Great. Next thing we're going to do is, when you're picking accelerometer readings from a device, there's a lot of readings coming. Some of them are noise, some of them come in form of different variables, magnitude, gravity, all these small noises. So we want to hold some of the noisy accelerometer signals that we'll get inside a variable that will be our buffer. We're just holding it. We hold the noise, and then just try to improve the accelerometer reading in a way that we're not just considering every noise that we get as a step count. So I know I've said so many complicated words, but simply put, we're just going to have a variable of type list, and it will hold values of type double, and then we're going to just give it a name called maybe window that will hold a buffer, a list of noisy accelerometer signals. We'll get to see how we're going to add them in the main logic, so don't worry about that. And then we just want to define the size of the list here to 20. So we're just going to hold 20 signals, and then whenever it reaches 20, we deduct the first one, first in, first out, so that you can create room to hold other noisy accelerometer signals that will come in. And there's a reason why we need this. We're trying to create that accuracy to be sure that any movement that happens on the phone, it could be of many reasons, but we want to purposely get for step count or something that represents a step has been made. Great. Now that we have that, we are done with our variables. Next thing is now we're going to call our two famous override methods, which is usually the init state and the dispose. So in our init state, there are two functions that we're going to call here. And then in our dispose, we'll want, after listening, whenever the app closes, we need to stop listening, okay? So we'll just call the accel sub and then we cancel. Once the app closes, it also stops listening, okay? Great. So next thing is, now let's look at our main functions, the functions that we'll really use in our application. We have our variables, we have the main override methods, we've just added them. Now we want our main function. So our functions will revolve, we'll have the first one where we'll be loading the steps for the current time, which is today, from the storage, and our storage is the shared preference. We'll have another function that will now save the steps to the shared preference. We'll have another one that will allow us to reset the steps again if you want to restart and start from zero again. And we'll also have another one that will now start listening to the device, to the accelerometer in our device. So now let's start. We'll start with our first function, which is loading the today's steps. So we'll have of type future void and call it load today steps and set it as a sync. And inside here, we're going to proceed to define our shared preference instance. Let's just import it. And then to just make sure that our context is mounted. Now we're going to just, once we read the steps from the shared preference, we want to store it in our step count. Remember this step count, we had set it to 0. Now we're going to put it as whatever has been received from shared preference. Simply put. So what we're just doing is picking it, and if it's null, we just set it to 0. So that's our function for loading the number of steps from our shared preference, and it's going to be executed at the point of init state. So we'll come here and add it here and call it as that. Next, we also want to, on today's date, let's define today's date. Date format. This is how you define or customize the format of your date. So we're just going to use that. Let me just import the intl. Great. So we already have our first function ready and it's being used in our init state. Let's work on our next. Our next function will be now saving to the shared preference. So we're just going to define future void, and we're going to create a function called save today's steps, and then we just create our instance and then we set it. Once we set it, it should be able to, we are going to be, once we get the exact steps from our accelerometer, that's when we proceed to call this function. Great. Next is we want to reset our steps whenever we want to just start from 0 again. It's good to have such a functionality, so we just call void and define it as save today reset today steps, and then we just call our shared preference instance, and then we proceed to remove today's date because we want to start from afresh, and then we set our step count as 0. So that's that. And then now we head over to the main functionality. This one I'll take my time with it so that you get to understand. So this is our start listening function. Now this is the one that now will allow us to get readings from our accelerometer in our phone, and then we'll be able to manipulate the readings and do some calculations. If you love math, this is very exciting for you, but you don't need to understand math. So the first thing is one of the constant or variables that affect the accuracy of accelerometer readings is gravity. So we need to define a variable that will hold the approximate gravity that we expect. And mainly we're going to use the Earth's gravity constant, which is 9.81. Before we go on with that, so the gravity constant is equivalent to the static acceleration. So there are two types of accelerations. We can have the static acceleration, and then we can have the dynamic acceleration. And what we're going for is a dynamic acceleration. So static acceleration is caused due to gravity. So accelerometer measures total acceleration including the gravity, and we need to remove that gravity. So we need to subtract the gravity constant so that we can focus on the dynamic movement, which is what we need in our case. And we earlier mentioned that accelerometers have so many use cases. So there are certain use cases that require that gravity, but in our case, in our use case, we do not need the gravity. So this will also help us in detecting now the actual steps rather than just the phone being still. Because when the phone is also still, there's some readings that are being passed or read. Great. So for us, we'll define a variable called gravity, and we'll give it the Earth's gravity constant for now, so that we're expecting the approximation to be that. Great. Now remember this variable that we defined, which is the accel sub, which is our sensor listener. Now we need to initialize it here. So we'll just call it accel sub. And then we're going to now call the accelerometer event stream. Okay, so the accelerometer event stream is a continuous stream of accelerometer data events. Remember the data events that I mentioned, they're coming with a data structure type of accelerometer event, each accelerometer event data variable, or the data that comes in, comes with three values, X, Y, and Z. So the accelerometer event stream is a continuous stream. So we'll be getting continuous accelerometer events data readings within it will be continuous. In short, that's what a stream is. So a stream is just like a water pipe where water is always flowing. So that's, instead of water, now just imagine accelerometer data events coming in continuously. Then whenever we get the data, we manipulate it as we need. Great. So now here, what we're going to do, we're going to call the accelerometer event stream, and then we're going to listen. We expect an accelerometer event to, let me put this properly. So we expect an accelerometer event, a variable or an object of type accelerometer event coming in, and that accelerometer event will be holding three types of values, X, Y, and Z. So for each event or for each object that comes in, we need to manipulate it, right? So this is where the fun part comes in. Okay, now we need to calculate the magnitude of the acceleration, and we are going to use a Pythagorean theorem in 3D. So it's a situation where we get, let me just write it in form of like in a comment. It's now we have three values that are coming from the event. So we have X, Y, and Z, right? Now what happens is we need to do a calculation where we get the square of x. How do we do this? Yes, we get the square of x, the square of y, and the square of z. We add all of them. Then we proceed to get the square root. You see? Then we get the square root of the total that we get. So that's how we're doing it. So we're going to perform this calculation so that we get the actual magnitude of the acceleration. So remember, we are in a stream, we're getting an event continuously. So whenever we get an event, we pick the values, we calculate it to get the magnitude of the acceleration. And then we proceed to, as we go on, you'll see how we're going to actually identify whether it's a step or not. If it's a step, we add it in our local storage as a step. Great. So this whatever I have shown here, it's equivalent to, we'll define a variable called magnitude of type double, and it's equivalent to getting the square root. This, you can get it in that math. It's this one. This is a package that has that specific method. So just proceed to do that, and then we have that. So this is the same as whatever I have explained up here. So we get the square of x, the square of y, the square of z, we add all of it together, then we get the square root, and that's the magnitude of the acceleration of the readings that we have received. Great. Now let's proceed to the next part, which is we now need to remove the gravity effect. Remember, we already defined the gravity constant that we're expecting. So we need to remove that gravity effect from this magnitude. So our new value will be magnitude minus gravity. Great? Great. Now remember we talked about a buffer or a type list that will be holding noisy accelerometer signals. This is now where we are going to work or use it. So we're going to define in our list, which we called window, we're going to add our value. So the idea is to add the values, and then we're going to smooth out the noise in the signals that we are getting. So take it like this. Imagine you're trying to hear a quiet sound in a noisy room. So if you listen to just one moment, it might be hard to tell what you're hearing. But if you listen to a few seconds and average what you hear, it becomes much clearer. So we're going to get values to 20, and then we're going to get the average of it to know the approximate value. We're going to get an approximate average value, and it's that average value that will help us understand whether it's an actual movement, is it a noise, is it a sudden has there been any change that has been made, is it actually it will help us detect whether it's an actual step. So we're going to hold these values to 20, and then when it reaches to 20, what happens is it will remove the first, it will use the concept of fast in, fast out. It will remove the first index so that it can accommodate the next value. So let me show you how that works. So we're going to do an if. We're just adding that logic I've just mentioned. So if the window dot length is greater than window size, which we set to 20, we remove the first one that got in, which was index 0, so that we can accommodate space for another one. That's simply how we're going to play around with that. Whenever we're getting values, we hold them to 20. But now we need to get whatever I had said, we need to get the average of these recent values. Now let's say, for example, the number of events have come in, filled the list to 20. We are calculating now the average of these values to smoothen the noise, okay? So it helps us set kind of a dynamic threshold for step detection. So we're trying to detect a step from these 20 values that we received on this window, okay? Another scenario will be, imagine you're trying to find like a pattern in a bumpy road. So if you look at just one bump, it might seem very random, but if you look at the average height of the bumps over a short distance, you can see the overall trend more clearly. So we need a number of values to be able to have that clarity and be able to get the actual baseline for the level of acceleration that we're getting. So that's the basic idea. So when the current acceleration value goes significantly above this average, so it's more likely to be a real step rather than just random noise. Okay, the next thing is, now that we have our list of values are coming in and they're in a list of type 20, there are 20 values. So it will only hold 20 values. If it reaches 20, it removes the first index so that it creates room for other values to come in. So the next thing we're just going to calculate the average of these recent values. So we'll proceed to create a variable called avg, and whatever this calculation does, it just does the basic mathematical creating calculating the mean of values. So we just add all the values and then we divide by the number of digits that are being added. For example, if you have like values like 2, 3, 4, so you need to add all of them, 2 plus 3 plus 4, and then divide by the number of digits, which are 3. You divide by 3. So that's just the basic mathematical way of calculating an average of values. Okay, the next thing, now we're going to add a buffer from this so that we can be able to avoid counting every small fluctuation as a step. So we're just going to define another variable called dynamic threshold, and we're going to take our average and add it a buffer of 1.0. Simply put, we're just trying to avoid counting every small fluctuation. Next thing, I'm going to define the current time that we are doing this. And then now we're going to proceed to now setting our condition for counting our steps. This is now the final part of counting our steps. So we'll proceed to just do a condition. Before I write it, let me just explain. So our condition is our current value crosses the threshold, 1, and 2, there's enough time that has passed since our last step. Simply put, that's what we're doing. So this will just help us to avoid counting false positives and being able to deduct the noise and the quick movements. There's some movements that are too quick that we're not considering them as steps. If you take a scenario where you're trying to jump over a rope, you want to make sure you only count a jump when you actually clear the rope, and not just when you make a quick movement that looks like a jump. That's not a jump, right? So we're doing those two conditions, which is equivalent to getting the height of your jump and making sure that it's higher than a certain threshold. That's what we're doing. So we're making sure that our current value crosses a specific threshold. And then number 2 is where we make sure that there has been enough time between jumps in our scenario where we are jumping a rope. Okay, so that's our second condition. So we need to make sure there's enough time that has passed since our last step. So all we do is do a condition with our if. We take our value, which is this, and then we check if it's greater than our threshold. And then we proceed to check also that current time, the difference between the current time and the last time it was we took the last record in milliseconds is greater than our cooldown milliseconds, simply put. So all we've done is we just taken our value. Remember the the readings that we get from our stream. We take that, we do our calculation, we remove the gravity constant, and then now this is just about creating an average of, or a threshold that we need to help us know whether it's an actual step or not. Then we just set our condition. That's our condition. If the value is greater than the dynamic threshold and the time is greater than 350 milliseconds, now we add our logic inside, where we now increment our step count. We just want to set this last step time as now, so that when we go back to this, when the stream picks the next values, it does the whole process all over again with the current data. And then we are saving our data in our shared preference, and we are done. Now the only remaining part is now designing our UI, which will be quite fast. So inside our scaffold, and obviously, where is it? Where does it end? It ends here. If we can add a set state just to make sure things are updated. Remember, we're incrementing the step count, and this step count will be represented on the UI. So we just want to make sure the new state is being displayed correctly on the UI. Now let's get into our UI. So we just have a simple app bar that says step count, remove the const, and then we just have an action there that will just allow us to reset our today's date, and then we'll just have our body. So for our body, we can define let's define it separately. So we're going to have a function of type widget and call it build today screen. So I've pasted the UI. It's very simple. So if we get to save that, you can now see the interface. So we just have the app bar, which is written step tracker. Then on the right, we have an action that will allow us to reset our step count. Then in the middle, we have our number of steps, which initially it's 0. Then we just have a section that has the goals, which we set as 5,000. Then it will also measure the distance and the calories in bare minimum. So if you look at in terms of calories, you're just taking the step count and multiplying it with 0.04. So we're assuming 0.04 kilocalories per steps. And then for distance, we're just taking the step count, you're multiplying it with 0.8 meters, and then dividing it by 1,000. So that's a simple calculation for those two. But it was just to create a better display for the interface and not just show the step count. So we can try and see if it works. Let's add this function that we created, start listening. Let's add it on init state. And we should be good. So if I save that, you can see. So I'm moving my phone and I'm trying to take a few steps. So for the minimal movement that I make, it's not counting. But the moment I take steps, as you can see, I'm taking a few steps, so it's actually calculating. But if I decide to just move the phone without just having a static acceleration like I'm doing right now, there's no addition, there's no step that is being counted because I'm actually moving my phone. Now I just moved it. It's kind of, there's movement there. But initially I was just creating that static acceleration, and you can see it's not counting. It's just stuck at 17. But if I decide to take a step, it's now counting again. So our logic is actually working. You can also try it by yourself. You can try and access the code and try and run it on your phone and see if it actually works too. Yeah. So I hope you have enjoyed building with me and building with accelerometers, mainly in Flutter. And obviously, with this logic, you can also try and run it on Wear OS and see how that goes. A wearable, that is, either Wear OS or Apple Watch. I think the interface will be quite friendly. Apart from the three cards that are below, you can try and tweak it now. So other than that, I hope you found it exciting and seen how powerful accelerometers are. We mentioned the many use cases that are there, so you can try and implement fall detection. Use accelerometers to detect a fall, and also once you hear a fall, you're able to return a feedback to the user and ask them, are you okay? And if they say no, you either do an emergency call for them. So you can create an app where when somebody is onboarding, they're able to add like an emergency contact, and it's just shared in the storage. And then when they use the app, you can also create the app in a way that it's actually running on the background, which also is quite sensitive. It depends, because there's certain, when it runs on the background, it might use an amount of battery. So you have to implement that, being conscious of such effects. But you can find a way in which you're able to listen to somebody's movements, and if you hear a fall, you're able to communicate with them. Even you can add a voice and ask them, hey, are you okay? If they say no, either by listening to the voice or maybe tapping on a dialogue, an alert dialogue, no, you're able to make an emergency call based on the contact that they have said. So now it's your turn. That's one example that you can do to implement the code further. And also you can decide to now allow a user to set their own daily steps. In this case, we just have a fixed one. And lastly will be maybe cloud sync support. You can try it. I would really love to see your version, how it turns out. And I'll leave my the Discord link down below. Hopefully this tutorial has given you some useful skills on how to build and how math also connects with code. So if you enjoyed it, don't forget to like, subscribe, and I'll see you on the next one.